Good afternoon, everybody. My name is Charlie Nicklin. I'm the Chief Executive of IAgrE, and I'd like to thank you all for joining our April or springtime lunchtime lecture. I'd like to welcome Craig Grant from Danfoss Hydraulics as our guest speaker today. Craig has been involved in the hydraulic industry for over 30 years and with IAgrE for nearly as long, about 25 years, I believe. He has worked for a number of the top global manufacturers of hydraulic systems and has been with Danfoss since 2018. In today's lecture, Craig will be talking about the next generation digital displacement hydraulic pumps, which incorporate some pretty clever new technology inside, developed by Edinburgh University. Craig's followed this technology closely and joined Danfoss to bring this to a commercial reality. So just before Craig starts, Sarah's muted you all. If you'd like to ask questions, please use the chat function at the bottom of the screen, and then at the end of the presentation, we can unmute you so you can ask away. So enough from me, over to you, Craig.
Right, thanks, Charlie. Thanks for that. And hopefully, technology allows me. So you have, let me just minimize that. You can see my front screen. Yeah, thank you for the opportunity to the Institute. Thank you everybody for taking your time out in a busy day. So pretty much I don't need to do too much of an introduction to myself. I think Charlie's covered that pretty well. And again, about the product itself, digital displacement. So I plan to obviously go through this as we go through the presentation to give a bit more background. So the introduction we've already had. We'll have a brief history lesson on where the product and the company came from, and just give a bit of an update on where we are now. And then really the crux of it is what is DDP, Digital Displacement Pump. So we'll do a bit of a technical dive into that, but not too deep. And try not to make it too salesy, because I just really want to sort of excite the audience about the technology. And then at the end, just give you an update on where we are with our product portfolio that we're starting to produce here in Edinburgh for the global market. And then, as Sarah and Charlie says, we've got the Q&A at the end. And I must admit, looking at the esteemed engineers online, I'm getting a bit nervous, but yeah. Let's see where it goes. So digital displacement came out of the formation of a company called Artemis Intelligent Power. And that was formed actually back in 1994. And they wanted to develop this next generation of hydraulics. So really, over the next few years, they sort of developed the concept and ideas to a sort of more mature state. And that resulted in 2008, they moved out of this sort of incubator facility at Edinburgh University into where we are just now, just on the outskirts of Edinburgh in Lone Head. To give it some concept, I think the two original founding members are still alive. One of them still very much involved on the board of directors. And at the same time, the technology that was coming out of Edinburgh was also very innovative with regard to wave generation. So companies like Polaris and Aquamarine were the breeding ground out of university. And this all happened much the same time. In 2010, due to the work that was being done by Artemis on what was wave technology and then moved into wind, they were acquired by Mitsubishi Heavy Industries, who wanted to develop a solution for large wind turbines. And we'll have a slide coming up with some projects to give you some idea of the work they've done for Mitsubishi. And also in this 2010 to 2018, the work on other projects to prove this DDP concept. In 2018, Danfoss bought the majority of shares from Mitsubishi. They retained some minority shareholding, and Danfoss got me in a free transfer to start this commercialization product. And in 2019, we had the first commercial release, and customer into the North American market, predominantly in industrial actually, although the focus for us will be very much off-highway construction equipment. So that's a brief background. So when I talk about the technology, some of the work that they have done, the main one I talked to you about was the wind turbines. So you can see here, top left and bottom right, these are 7 megawatt wind turbines. One was in Hunterston and one was placed as a floating turbine off Fukushima in Japan. Now, actually, what's happened now is both these are being decommissioned now. The technology moved on, the desire for such concepts. I think what happened was Mitsubishi bought Vestas and took the technology in a different trend. But the image in the middle is actually the digital displacement pump motor. So it was able to take the rotating energy and convert it into obviously a signal to go into the grid. Other technologies that the Artemis team have worked on is drive solutions for, and the top middle is the bus, which has now found a home in the Commercial Vehicle Museum up in Fife. And the picture to the right is our hybrid BMW 5 Series, which we still have here in Edinburgh, parked out the back. But long before I was on board, this was doing tours of Europe, and predominantly in Munich, BMW arranged the closure of certain parts of the city to allow the car to be driven on public roads. So these were the sort of technologies that went on in the background. In the bottom left is probably the first one where I started getting more involved. The project had been ongoing, but this was for diesel railway, and the desire to go to lower emissions was clearly the target for the rail industry, and electrification was a clear path. But the infrastructure wasn't there and wouldn't be there for many, many years. So they were looking for other technologies to try and reduce emissions. And on these railway units, there's a diesel multiple unit sits under the carriage. There's usually 2 or 3, depending on the type of class. And these, through the diesel engine, supply power to a generator for the electric supply and to the cooling system. So we were able to show quite high efficiencies and productivity savings, that we could save ScotRail on this occasion around 10 million tonnes a year of CO2 and reduce their fuel bill. Now, you would have thought they would have bitten our hands off at that, but the challenge for the rail industry is it is so political, because you have ScotRail or Network Rail with the infrastructure. You have the franchise owners like ScotRail, Northeastern, people like this, and then you have the asset owners that actually own the rolling stock. So you have to communicate across all 3, and all 3 are very risk averse. And despite our best attempts, and we actually got funding, approval and funding from the government to develop another project, but we just could not get any of these 3 bodies aligned. If you take ScotRail, for instance, they were on a, pardon the pun, shaky nail about losing their license, and that's obviously came to fruition anyway. But they wanted to stay away from anywhere that could have a negative effect, even if there was a positive story to tell. So that's enough about the sort of technologies that we've worked on. What we're very excited about is, obviously we have this location here in Edinburgh on the bypass, but in January 11th this year, Danfoss acquired the remaining shares in Artemis Intelligent Power. So the company is now 100% owned by Danfoss. And the new plan is we will move to a new facility by the end of next year, just about 4 miles away again on the outskirts. And this will be our headquarters, innovation hub, and R&D facility. So when I say an innovation hub, Danfoss has other business units, and one of those is Editron, which is electrical components, drive motors, inverters, and they have a contract in the UK they've just secured. So they're going to share our facility. So, and there's a clear alignment between both parties, because electrification is digital displacement's a clear enabler. So I think that's probably enough about a bit of background and information. So to cut to the chase, what is a digital displacement pump? And I think this slide here, and it is slightly animated, but it may be a bit difficult to follow. But if you look to the picture to the left-hand side, this is a typical cutaway of a variable displacement pump. But you can see this was patented almost 130 years ago. So the technology actually in current variable pumps has not changed that much. The concept is the same. You know, a rotating group, some pistons, a cradle, and shaft. So you have a lot of mass there to rotate at any point and accelerate and decelerate. Technology has evolved, so they may be using different materials and maybe a different type of control, but at its heart, it's still a moving mass. If we now go to the right-hand side, this is a cutaway of a digital displacement pump, and basically our pistons are arranged, 12 pistons are arranged in a radial fashion, and they're individually controlled, which allows us to control the displacement of the pump as it rotates. And I'll start the animation in a minute, but what we're doing here is we have an eccentric shaft where the pistons are located on, and as the shaft rotates, the pistons get to a point what we call bottom dead center, and at that point we would fire the coil. We don't energize it, we just pulse it, and that allows us to close off a poppet valve, which allows us to then start pressurizing the chamber, and that goes off to the function. So if I now show that in the animation, if you follow the picture at the top, you can see piston bottom dead center, and then we fire or pulse, and that allows us to close the chamber and put the fluid, just like that one again, allows us to push the fluid out and then onto where the function is required. So that is the clear and simple essence of digital displacement. But obviously there's a bit more to it than that. So this is the overview of a digital displacement pump. And as I said, we have 12 pistons arranged in a radial fashion. And these are grouped together in stations, so that you have a group of 3 pistons here at the right-hand side. There'll be 3 at the left-hand side, 3 at the top, and 3 at the bottom. And we group them together and we call them pumplets. We like to make new names up, and one of those names is pumplets. But if you just imagine, this is just like a small pump within a pump, is probably the simplest way. Each cylinder is 8 cc's, so 12 times 8 gives us 96 cc's. And then we have this, you can see here another cable coming off top and bottom. So we have sensors on the pump, so pressure sensor, speed, rotation, and temperature. So the pump's fully sensorized. The grey box to the bottom is the controller. So while the pump is the heart of the machine, the controller is the brains, and they coexist. One cannot function without the other. But what this product gives us, compared to traditional technologies, the response time is around 30 milliseconds, which makes it very fast compared to traditional technology, which allows you to get good repeatability and good robotics level control. The efficiency, and I'll come to this in a slide coming up, but we have got the highest efficiency across the widest speed range. And on this unit, what we're actually showing here, we have 2 versions, and I'll cover this again later. You can basically take a single outlet pump. So we have one inlet, one outlet. So you take the full displacement out to the function. But in this one, what we're actually doing is we have P1, P2, and P3. So these are three individual separate outlets. So they're independent of each other for flow pressure and the control method. So P3 is slightly larger because you're taking the top group of three valves and the bottom group out. So you're basically taking half the displacement out of the P3, and then remaining outputs, you're taking a quarter through P2 and a quarter through P1. So where can we apply digital displacement? So we apply it in energy sensitive systems where you want to, maybe a battery driven machine where the cost of batteries and duration of operation can be quite sensitive. Productivity driven machines such as excavators. So if you can produce, if you can make them more productive with the same amount of fuel being burned or potentially less, then that's an attraction. And highly dynamic systems such as presses or injection molding, where you have a desire for high pressure, low flow, and then low pressure, high flow, low pressure, low flow, high pressure type of functionality with this response time, where you have to switch from one concept to another. So that's some of the key features of digital displacement. And just for the engineers amongst us, we always like to look inside. And this is an exploded view of the pump. And again, the pictures to the right-hand side show the triple outlet at the back, and then this is just the single outlet pump. But we have the main housing with the drillways done in a certain way, depending what end cap we're using. We have obviously the end cap itself, which could be the single or triple outlet. It has the portings for sensors, and we can take a through drive, which means we can put another pump, DDP pump on the back, or we could put a variable pump or a gear pump on the back as required. We have the shaft, which has the eccentrics offset with the pistons associated to it, and these are the capsules with the coils that go into the main body. So that's an exploded view of the pump itself. So we'll come up against this in a few slides, but we've done a lot of work. We see digital displacement. The real marketplace for this is in hydraulic excavators. And we've invested heavily here in Edinburgh and across the globe in buying machines ourselves to do conversion projects to prove technologies. But what we found out is if you take a traditional 16-ton excavator, it never tends to run at full load. So you tend to find that the engine will be running at part load. So your output to your pump is at a certain level. And we know that traditional hydraulic variable pumps are not as efficient as DDP. So there are losses there. And then you're then going through a main control valve. And again, you have a high degree of losses there just because you're throttling the desired out to the end function. And then we also lose the capability to recover energy from that. So what we're saying here is, by the time you get to the bucket, the amount of power you're putting in and what you actually get at the bucket, the overall system is only 30% efficient. So how do we tackle that? And the way we've approached it is trying to do it in 3 steps. And the small diagram at the bottom gives some idea, but the next slide will explain this in a bit more. You may recall we like to make new terminologies up, and the one that we have is SA1, SA2, and SA3. And SA just really stands for system architecture. So this is where we start to potentially play about with the insides of an excavator. So an SA1 in its purest form is just really we're looking at the standard hydraulic pumps and using digital displacement as a more efficient solution. We can start to reduce the losses here and potentially increase productivity. With SA2, we start to move into looking also at where the valves, the dissipation of energy through the throttling and the way they're currently configured. So by some small changes and adjustments, we can start to improve the efficiency. And then SA3 is sort of next generation, where instead of a pump, it's a pump motor, and it allows us to recover energy. So what drives us forward on that? Might have helped if I'd done this. So again, just to reiterate, SA1 is just talking about mainly the pump itself. We have some engine interaction if we can, depending on the operator, because we can extract more efficiency out the diesel engine, because we can run so close to the horsepower of the machine. In traditional technology, there's always this lockdown and the fear of stalling. We can get pretty much anti-stall and as such extract more power out the system. So SA1, we were expecting 20% on our simulations, which is always the first thing that we do. And what we actually achieved was 20% fuel efficiency. So we improved fuel efficiency by 21%. When we go to SA2, as I say, we start to look at the way that the circuit is designed and trying to make it more efficient by using the efficiency of the pump and the multi-outlet capability. And that means we were able to measure up to 32% fuel efficiency. And then looking to the future, simulation to us suggests that we could achieve in excess of 50% efficiency compared to an existing excavator if we're able to start recovering energy through a more intelligent system, maybe actually almost removing the main control valve if we can and driving it directly from the pump as the power and demand source. But the key part to us is the graph at the top right is, if we go to this SA1, we want to move from point 1 on the graph to point 2, which is the BSFC. So we get more energy out on a more fuel efficient system. So efficiency, I keep going through this word. So this really sort of starts to highlight where we are with regard to existing technology. So if you take current technology, which is the red and blue graphs and the cross graph underneath the green line, you tend to find we still give an efficiency uplift of 4 to 5%, depending on the pump you're using at its corner condition. And that's where the machines are at the most optimum. But going back to the earlier slide, we know machines tend to work at part load. There's idling sections, they're not always requiring the full power capacity. So as such, it means your pump is working off displacement, so it's no longer at 100% displacement, so it drops down. So if you go to 40, 60%, your figures start to drop right off. Whereas with digital displacement, because the way we are configured on the valves and the way it's radially done, is even down at 20% displacement out this 100cc pump, we are still giving an efficiency of 90% on that displacement. What we did see in some marketplaces was the desire to reduce fuel and noise, so a drive towards first putting larger pumps on. So this is 100 cc's, and what we found, customers were maybe going to 120 or 140, which meant to get the same flow they'd run the diesel engine slower, which is fine when you're up at this condition, it's perfect. But as we said, you're not always here, and if you've now got a bigger pump and you're working at part load, then that displacement, instead of being here on 100cc, with a larger pump, you're probably down at this area or lower. So that quickly lost favour within the marketplace. With regard to losses, we've not invented the no loss pump. You know, we still have mating faces, seals in there, we have bearings, but you know, in comparison to existing technology, you can see here that compared to that existing technology, we step up in a straight line because it's all about just switching on the valves. But when you're sitting at high idle load, where the pump would tend to be on a variable pump, where it would tend to be idle pressurized. So that's sitting at 200 bar, pump running at 150, 1500 RPM with a 100 cc pump. In the worst case scenario, a variable pump could be putting out close to 6 kilowatts of power to do nothing. It's just sitting there, burning that energy off and creating that heat. With digital displacement, we're 600 watts. So again, these are the areas where we start to claw back a lot of the efficiency gains. So when we look at the work that we've done, we have this is our own machine here in Edinburgh. This was the first machine that we converted, and if you remember the terminology I called, it was the first one that we done with SA1. We just purely put the pump on there. This is now moving into what we call SA2 Architecture. And what we're doing here, this is a tandem pump down here at the bottom of it's a JCB GS160. So we took the existing, I think it's Kawasaki pump out, put our pump on, and this is a tandem pump that has 4 outlets per pump. So it's a different version end cap. That then allows us to take all 8 ports up to this ganging block or elastic valve block. And then what that really allows us to do is we can now switch those valves, these red dots, if you imagine these are switching valves. And we can either send, as it shows here, maybe the left-hand pump, all the flow off to service 1, and then all the flow from the right-hand pump off to service 2. Or we could give all the flow to service 1, or we could give all the flow to service 2, or any variation in between, depending where that flow or pressure demand is required. So that starts to allow us to really extract those high efficiencies up, 30% efficiency gain, because we are just giving out the right flow for the right function compared to existing technology. Because in current excavators, it's a 2-pump system, 2 outlet. So we are just mimicking that, but utilizing the multi-outlet pump capability and switching valves to direct that flow accordingly. We developed what we call a white paper for this, and that was delivered to esteemed engineers at the IAgrE, which was held in Germany back in October. And the engineers involved presented the results and the findings to the point where this actually got the gold award, the top award for the presentation at this event. Again, that was quite an experience for us. So as I say, we're very much focused on the excavator market, and what we have here is we have these tandem versions. And the picture here shows the 96cc in its tandem version, and it could be 2 single outlets, or it could be the multi-outlet. But we tend to call this the SA1, just a pure pump swap. And then we have what we call the SA2 option. And this is where we have, again, the same pump, but instead of the single outlet, we have the 4 ports. And those 4 ports would go into this manifold block, which is close coupled to the pump itself. And then it allows us to send the correct flow off to the correct area. And again, we have these pumps out on field trials with both in excavators and on wheel loaders. We have a project on a mining loader at the moment. So it's like a wheel loader, but it goes underground and it's battery driven. And then we're just talking about a new project for a forestry skidder, where they're going to utilize a single DD pump. So we are very much heavily focused on excavators, but we are getting more experience in other markets where this flexible pump brings a lot to the marketplace. And then the final picture here is what we're calling our DDP 180D. This is a back-to-back pump. It uses the same concept, so pistons on a radial fashion, but this time there's 15 of them. And it's two pumps that are mounted together with a single inlet, so common inlet, but we'll have two outlets at the start. And that means we've got 180cc at the front and 180cc at the rear. And that allows us to go into much larger excavators. And what the technology will allow us to do as well is on the eccentric driving the pistons, we can actually change the offset, which means we can go down to a 150cc version or a 120cc version if this customer so desires. And then we'll bring out single versions as well. And the technology, the valve technology is changing from the original to this new version, because this new version will allow us at some point, if there's a clear commercialization needed, to go to a pump motor technology. So these valves can obviously then work in both directions, whereas the current pump can't do that. So this picture is of our other machine, which at the moment is currently based in Ames, Iowa. It's a CAT state-of-the-art excavator, so it uses current technology, electro-hydraulic controls and joysticks, electro-hydraulic controlled pump. But again, we were able to improve this as was shown in the figures before. But we see that that this is the technology that allows us to drive forward into the excavator market. In fact, this machine is potentially now being lined up to be transported out to, we call them ADCs, they're application development centres. So it allows us to take customer machines, we buy them, and then we optimise them using Danfoss products. And it allows us to showcase solutions away from a customer, but we can do customer collaborations as well. And we have 3 of these around the globe. One in Nordberg, which is the headquarters of Danfoss, and we have this one in Ames, Iowa, and we also have one in Hainan in China. The one in Iowa, it's a fully functioning test area, so there's various inclines, etc. So we actually had to build a hill to do the tests for incline tests. And we now, if you've never been to Iowa, you probably know how flat it could be because of the agriculture. We have got the highest spot in all of Iowa in our back garden because we had to create it by this facility. So if you do want to know more, by all means, feel free to reach out to me. But there's a good repository online called digitalplacement.com, and on there, if you think back to that very small animation where I was trying to show the pump rotation and the shaft and the pulsing of the cylinders, there's a full suite of those animations. We also have podcasts, so talking heads as well. We have videos showing the machines in action, and again, these white papers. So if you really feel lost, you want to know a bit more, you've got a couple of hours to kill or a couple of days to kill, there's a lot of information on there to learn more. But I think that now brings me to the end of the presentation.
Okay, thanks for that, Craig.
Oh, okay. Thank
back
you.
on. Yeah, so, excuse me. I've got a pre-sent question from Alan Plum, who couldn't join the call today, but he'll obviously watch it afterwards. It's more of a general question. I'm not sure whether you can answer it or not, but it's about, is there a potential to use hydraulic power to improve safety as well, more replacing PTO shafts and driveline components on machinery? And also, what's the uptake by manufacturers, given that hazards should be designed out of machinery? So it's a very health and safety orientated question.
Yeah, I think that the pump itself is I mentioned earlier, has the various sensors on it, so it starts to lend itself to sort of autonomy, robotics. You can know exactly what the pump's doing. So I think that there is a potential to improve the health and safety. Maybe not to the level that you can take away rotating shafts. I think that's still going to be a key part for us. We need some sort of prime mover. But with regard to uptake from the market, as I mentioned, we are in production with our first generation pump, which is mainly industrial. And it's a sort of high performance test power unit, for sort of like Formula One cars where they do the shake test, the chassis shakedown test, etc., or S-Quake simulation where you need a high resolution. But as I mentioned, we are in sort of field trials with some very large OEMs around the globe. Primarily my role is in Europe. I have a colleague in North America, but I'm also dealing with Asia Pacific as well. So as I say, it's pretty much on a global scale now.
Okay. A couple of questions that I'll put up. Is there any plans? I mean, they're quite large pumps, 2 times 96 cc. Is there any plans to go smaller for smaller excavators and off-road equipment? And also, how does the cost compare to a normal variable piston pump?
Yeah, it's a lot more expensive. That's as much as I'm saying that one. Yeah, there is a
percentage wise.
Even that, but we approach it on a value sell, because we are bringing something to the market. If you look at these big OEMs, they're setting themselves very tough targets on CO2 emissions for their products. And yeah, we believe battery electrification is one of the drivers towards that. But they're quickly realizing they have to change the hydraulics as well, because as I showed in the excavator, they're still burning a lot of energy. So even if it's not fossil fuel, we're still using up a lot of battery energy. And batteries cost for industrial machines just now are about 500 euros a kilowatt hour.
Yeah.
And if you can reduce that, you can save a lot of money. So with regard to going to a smaller size, at the moment, the question is quite simply no. But if you came along and said, class, want to buy a 46, and there's 100,000 units a year, I think we'd be interested. But there's no plans at the moment. It's pretty much start with 96, going up to the 18360 version. But what the multi-port pump gives you is the ability to look at maybe an existing system where you have a couple of prime movers or a prime mover, maybe 3 pumps, that you can start to consolidate that. So you might have 3 pumps that make up that displacement. And again, the efficiency of the pump means on one application, the customer was using a 140 cc pump. And we were able to use, because of the multi-port technology, a 96 cc more efficiently without loss in productivity.
Okay. Yeah, I suppose my question with the sizing was, with that in mind, about electrification tends to be focused on the smaller equipment at the moment, simply because of the cost of batteries on large equipment. Michael, got a question? You want to unmute yourself?
There we go. So from the simple mechanical engineer's question, things are great when they're running, but things go wrong sometimes. So how reliable are these units in what are going to be very arduous environments?
Yeah, it's a common question. What is the durability? And we're obviously basing the design is to offer the same, if not better, durability. Show that really it's the bearing life that is the driving force on the lifetime of most pumps, and that will be no different for us. Yeah, we have an electric controller, but it's robust. It's designed for that marketplace. We have, as I say, units out there that are gathering up on top of the hundreds of thousand hours we've done on our own test rigs that are building up thousands of hours without any clear failure modes coming back. Yeah, we get niggles here and there. We have one just now where when it was installed by the customer, they had a cloth rag on the inlet. Cover your ears, John, you're not like this. They had a cloth rag on the inlet while they were moving it, and somebody forgot to take it out. The pump's been working for 1,000 hours. Yeah, we've had some issues, but nothing, the pump still kept running. But it is new technology. We've got a lot of barriers to break down. And these sort of questions like the durability and robustness will always come back to us, and we'll answer them as best and as honestly as we can for a new technology.
Thank you.
Rupert.
Hi, Greg. Thanks, Charlie. Yeah, my question was, I was looking at the animation of the eccentric pistons and how it drew the oil in from the suction port and then closed off the outlets to create the pressure on the outlet.
Yeah.
Obviously, that lends itself to an open circuit system, which majority of excavators are, but is there a possible way of creating a closed circuit version of that so the flow goes back to the pump and then you can flow the oil out one way or the other? Yeah, like a closed circuit pump. Is that in focus, or are you just looking at open circuit versions?
At the moment that the commercialization is about an open circuit pump, the history on the Artemis pump has obviously been very much on closed loop systems as well. So we understand that we have the technology if we want to do it. But what we can actually do is we actually have our own forklift truck, which we've taken the torque converter off. We've put a single DDP with a multi-outlet, and we control that again through that that switching valve block. We can direct the flow to either the transmission or to the work function. But when we send it to the transmission, it then has to go through another block which has all the safety valves and switching valves to ensure that it's driving the right direction. So we can use it to do propel functions, and we show a lot of benefits in this technology because it allows us, if you think we can send the majority of flow to, let's say, propel when you need it, you're driving towards a pile of earth, then when you need the flow and pressure for other functions, you switch it over to the work function in order to move the pile or whatever you have on the end of the blades. So we have experience with it. We are sort of trying to test the market, but it's not a proven technology. It's still very much R&D. There's safety functionality, that has to be considered. It was never designed for that. So again, if somebody came along, such as a forklift truck market, and said, we want to do this, then we would do a collaboration project. But for the moment, it's purely an open loop pump.
Okay, yeah, thanks.
Thanks.
Richard, you have a question?
Yeah, thank you very much. It was a brilliant exposition, Craig, and I remember when you first talked about it, you had me thoroughly confused, being my idea of a pump is roughly a lever and a cylinder and an O-ring or something like that. I did hear a few years back of a project I thought also came from Edinburgh of not using flow in hoses to operate things, but actual pressure waves. Do you know anything about that?
No, I can't. It doesn't jump to mind. Time is not on my side. It doesn't ring any bells at this point. But I can certainly ask the guys that have been involved from the start here if they've got any information.
It would, I mean, at the time we were looking at, well, what was effectively a breaker application. And so instead of needing whacking great hose for return oil to get the pressure down, that sort of thing, you could do the whole thing on a couple of 1/4-inch hoses and get a lot of performance.
All right.
Well, that was what they were saying, but it's all gone quiet. So I wondered whether you'd perhaps been near to somebody who might know about it.
I'll make some inquiries. I can't say I've heard anything. I'll maybe ask John Savage. Have you heard of this?
No, I've not heard anything about that, Craig. Yeah. No, not at all.
Okay.
Oil still seems to be moving in pipes.
Yes. Okay. I'll see what I can find out, Richard.
Well, thank you very much, and particularly for those institution members here, we recall when back in the Bosch days when you helped the Young Engineers Competition get off its feet. So thank you for that as well.
No, thank you. It's good to look back in that and see the involvement. And again, that's part of this, you know, sort of reaching out in these lunch and learns is to keep that knowledge base going, both with the engineers that we have and those that are coming along behind us. So, you know, I appreciate the opportunity, because who knows where these young engineers will go. And then they may reach out to us more senior gents for a bit of guidance. And
we can hope.
Yes.
Okay.
Okay. Thanks, Richard.
Martin, you have a question?
Thanks, Charlie. I was just wondering if you had measured the fuel savings related to such units that you fitted to the engines. And, you know, has that been measured? Really, you're looking at efficiencies there, which is typical of pump situations. Just wondering about the climate now that it's become so focused with the pandemic and the situation with changing fuels possible for engines, you know?
Yeah. So there were some numbers put up there on what I was calling SA1 and SA2. So SA1, it depends on the type of machine, you know, the technology, negative flow control or positive flow control. And then SA2 means we're doing more around the valve block. So this allows us to achieve these, you know, the 20 and 30% fuel savings that we attribute that are on the websites. So yeah, we can obviously put that into, you can express it in so many ways. The industry wants to look at it in different ways. So is it litres per hour, is it litres per tonne? You can throw many different numbers at it. So we've just expressed it as an efficiency saving. And it is predominantly around industrial, you know, diesel engines. But yeah, with the trend towards electrification, you know, I mentioned the cost of the batteries is fairly high. And at the moment, they're in this dilemma of how big a battery do you put on a machine to get a full shift, and can it do a full shift at full load, or is there a trade-off? And that's where we see again DDP sort of trying to drive towards, you know, helping to either reduce the battery size, because these things are not particularly small, so it's a challenge fitting them on machines, the cost involved, or it's a case of maybe maintaining the battery but actually getting a full shift. So there are efficiency numbers on the website. It's just if we had to sort of repeat every one that we've worked on, you know, the machines that we've bought ourselves and the projects we're working on just now, they each show different ways, because, you know, each machine is slightly different in its own concept, and how intrusive we can get to the system, and how closely we work with the OEM. With one, we had almost like open book, here's your engine controls, etc. With another, no, there's a signal from our motion control unit, and that's as much as you'll get. That restricts some of the benefits we can get from the way we can control the pump. So I'm not sure if that's answered your question, Martin, but I'll be happy to send anything specific if you had the specific requirement.
Okay, thank you.
Just no more questions. Probably just the last question from myself. From a equivalent size piston pump, are there less moving components in this? Because it seems to be sort of a simpler mechanical setup, obviously with a bit more sophistication with electronics and sensors and so on.
I mean, a 100cc pump would probably have 9 pistons, so we have 12.
Okay.
But they have a rotating group, then they have a cradle and swash. So I think maybe we have the edge. I've never actually sort of sat and dismantled one pump, dismantled ours and said, there's 120 components there and 120 components there. It's probably a good analogy to do that. Maybe the less moving parts, the more the less to go wrong with it, I suppose.
Well, yeah, that was sort of my thinking really. That it's the mechanical bits that generally go wrong, and even when the electronics go wrong, it's the mechanical bits of the electronics that's gone wrong.
I mean, one of the if you imagine on a traditional technology, if a piston fails on a variable pump, it can maybe just limp along slightly, and you may see increased drainage, maybe an increase in temperature, but it could result in catastrophic failure. With ours, we're able to monitor through the control system. We know exactly what's happening at each valve, and what we can actually do is, if we see a valve go faulty, the controller can itself decide, I will not fire that valve. There's something wrong. There's an error message or something wrong there. We'll take that out the loop. So you then, instead of having 12 pistons, you only have 11. So you have a reduced capacity. But unless you're working up at that corner condition, then the operator will see no difference, even in the loss of a control valve, until it reaches saturation point. Now, I'd probably say at that point, would he notice any difference? I'm not sure he would.
Yeah. Okay. Interesting stuff.
Can I ask a question, Charlie? Craig, in this world of where pumps are very expensive, and obviously from a dirt sensitive point of view, we always consider them to be the thing that we need to protect. What is the recommended cleanliness level for this style of pump in operation?
I'd need to look at the data sheet, but it's equivalent to existing technology. I know from speaking to my colleagues, we've done duct tests to quite a high level, and obviously in going to the market, certainly with the big OEMs, you have to go through a raft of tests, basically trying to test the pump to destruction. So I would say ours is comparable, and it's probably a bit more dirt tolerant than traditional variable pumps, based on our experience. But yeah, I mean, it's in our what we call TI manual. It's not a number that's straight off the top of my head, because the ISO codes changed, and when they went to move to the 3 version, I lost where it was again.
Onto AS459. Do you think what you've said there is because you are not using a sort of swash plate mechanism, and therefore you're using a sort of open close valve process, which obviously is, to a point, can be self-flushing? I think there are some benefits, but as you probably know yourself, with a variable, with the swash plate, over a period of time, you could score it with a particle going through, but then over a period of time, it probably, shouldn't use the word self-heal, but it can repair itself slightly just by gradual wearing down the port plate. Okay, I mean, my final question's got to be, when we met just over a year ago, Craig, I asked you this same question, and that is, when are you going to have one brought down to the National Fluid Power Centre so that everybody can see it?
Well, it was there a year ago. I brought one down. It was a cutaway one.
I know it was, but you took it back. Remember remember on a good year, there's 2,000 people coming through the National Fluid Power Centre.
Yeah. No, I very much appreciate that, John, and it's still very much on my agenda. I see the real benefit in it, in having our technology. I think there's just maybe a bit of nervousness that it's slightly out with our control and it's there amongst competitors' products. But yeah, we've got to be less sensitive in the future and just get it out there.
Well, there's a bit of everybody's here, as you know.
Yeah. And I'd love to see your pump room with a DDP sitting alongside everybody else's.
Yeah, me as well.
Yeah.
Thank you for that, Craig.
Okay, thanks, John.
Okay, so we're just nearly up to an hour, so I'll draw things to a close. So thank you, Craig, for taking some time out to present today. Really appreciate it. It's great to hear about some of the commercial developments going on in the hydraulics industry, and I'm sure people find it really interesting. So thank you for that. Just before we close, I'd like to thank you all for joining us today and hope you will join us for our next lecture on the 11th of May, where we'll be joined by Dr. Andy Scarlett, who is going to talk about one of the machinery industry's most favourite subjects, which is tractor and trailer braking, which goes on forever and ever. So all that's left to say is thanks again for everybody for joining, and see you next time.